this change of base of logs as something kind of slightly different. Because if we take a look at this vertical expanse, or this base 4 log, if I apply a vertical expansion to this log, okay, so I get log 2, sort of 2 log 4 of x, I can apply this power into the log. And I think I showed you a little bit earlier that there is this kind of shortcut. If I power the base and the argument the same, the logs don't change. Okay, and I'm going to just briefly show you why. Because really what are the parts of a log? There's a base, there's an argument, there's a power. Okay, and so what I'm saying here is if I change the power on the base and the argument, I don't actually change the power of the log. Okay, so starting with this, here's my log base log, my argument, my exponent. And I'm going to change the base of the powers on these, and I'll show you that the power y doesn't change. Okay, so I'm going to rewrite this as an exponent, like that. Okay, so I'm just going to write this slightly bigger like this, and if I do this, if I power one side of the equation by 2 and the other side by 2, do I change the value of this exponent y? Well, no, I don't. And so that's what's happening here. If I power this by 2 and power this by 2, I don't actually change the value of the log. This log here is the same. I don't change the value of the exponent y. So if I then understand this concept, then really I can change that power to anything. I can change that to 4.5 here, 4.5 here. I don't really change the value of y, okay, because I don't change that equation. I don't change that equality whatsoever. Okay, so in general then, I can change that not only to squares, I can actually change that to like a some power, random power z, as long as I do the same to the other side of the equation. Because essentially, I'm not breaking any math rules. I'm keeping the equation balanced. I'm keeping the log in balance if I do this. Okay, so this is a proper I can use. So how does it work here? Well, if I have these two powers like this, well, I can just change the base. It just changes the base. I can square root both the power, the argument, and the base and do that. So my vertical expansion really is a change of base. And so I can show this as well. I can do this in reverse. This change of base must be some vertical transformation. So if I write this out, okay, I can either change the base, as I did in the previous example. I just changed the base to base 2. But I can do this. I can cube root this and cube root this. Okay, so I end up with log base 2 x to the 1/3. That 1/3 gets pulled out, and I get 1/3 log base 2 of x. So that change of base from base 2 to base 8 really is a vertical compression. So there are these different transformations. If we can understand how the logs are, we can use the log algebra to manipulate things. We can see how these things change. Okay, I'm going to show you a couple others, and I'm going to show it on Desmos and show you that, in fact, a vertical shift can be shown as a vertical expansion. Okay, and it depends on how we frame it, and it's to do with this. Okay, so this is a separate issue here, so I'm going to move all that out of the way. If I have log base, let's just base 2 of x, okay, and I do this. Sorry, I missaid that last statement. A vertical shift can be expressed as a horizontal compression or expansion. Because if I do this, horizontally compress, right? This is a horizontal, the transformation here is a horizontal compression by 2, okay, or by 1/2. this is equivalent to this. Log base 2 of x plus, I can split off this like that using a log property. So this can now be expressed as, instead of a horizontal compression by 2 or by 1/2, I can say this is a vertical shift of +1. And they must be equivalent. They're the same thing. Okay, so this horizontal compression of 1/2 based on this times 2 here is the same as a vertical shift of +1 because we can transform it using some log rules into a +1 log. Okay, and we can actually see this. And I'll show you the graph of this in the next video.